Thermodynamics obviously means using heat to move stuff. Thermo is heat and dynamics is motion. So using heat to move. So it's been the dream from long time back. We could make something move on its own. And finally it came to pass because of a French engineer. I think I've talked about this, Sadi Carnot, who made it happen. Now before we get to understanding how the gasoline engine works, we got to get some basics. Any part in physics is built on laws, and in thermodynamics there are 4 laws. The first one is called the Zeroth Law, because the first one they called it the first law, but then they got a more basic law, so they had to call it the Zeroth Law. And I'm just going to state the Zeroth Law because I've not written it down. According to the Zeroth Law, if you have 2 systems in thermal equilibrium with a third one. So let's say you have systems A and B that are in thermal equilibrium with a third one, C. So that's in thermal equilibrium, they are in thermal equilibrium, which of course means that A and B are in thermal equilibrium, right? So that's why it's a very basic law. Now what is the meaning of thermal equilibrium? It means same temperature. So you got to get you will get a lot of information today, a lot of concepts, and of course you need to understand each of the concepts. Thermal equilibrium means same temperature. That is the Zeroth Law of thermodynamics. And in this chapter, today we'll talk about the first law of thermodynamics. The next day, which will be our final day of lecture, we'll talk about the second law of thermodynamics. And that's where you'll understand how these laws can be used to build up an engine that moves on its own. But we take off from specific heat. Does anyone remember what specific heat is? It's defined as the amount of heat required to increase the temperature of 1 kilogram of a substance through either 1 degree Celsius or 1 Kelvin, right? 1 kilogram through. But when you talk of gases, we do not usually deal with a kilogram, we deal with moles, isn't it? So we're going to change the definition a little bit. We're going to say it's the amount of heat required to change the temperature of 1 mole of a gas. So instead of 1 kilogram, we're going to use 1 mole. Therefore, it's called molar specific heat capacity, because we're dealing with 1 mole. Now the second thing is, come back to reality, don't just be, yeah, that is reality, switching off. When you heat a gas, it's not like heating a solid or a liquid. What's the difference when you heat a gas? What's the difference? When you heat a solid, basically, though it expands, the expansion is negligible, isn't it? But when you heat a gas, you cannot neglect the expansion. Therefore, when you heat a gas, you can heat it in 2 ways, under 2 conditions. You can either keep its volume constant, like if you have a closed container and you have a gas inside and you reheat it, the volume is not going to change, right? What's going to change? The pressure. Wouldn't the pressure increase? And what about the temperature? That'll increase too. So there you're heating it under constant, help me out, constant what? Volume. Or you can have something like a cylinder, which I'm going to show you, a cylinder fitted with a piston. And then, okay, so here you have the cylinder with a smooth, frictionless piston. You have 1 mole of a gas here, and you heat it. Obviously, the piston is going to move until the pressures are balanced, isn't it? So in this case, you're heating it under constant pressure. Now, I want to ask you, in which one of these 2 cases would you need more heat to increase the temperature by 1 Kelvin? In which one of these 2 cases? Is it when you heat it under constant volume, or you heat it under constant pressure, that you would need more heat to be given to increase its temperature by 1 Kelvin? That's an easy question to answer. So when you heat the gas under constant pressure, where the piston is free to move a part of the heat that you're giving it is also being used for expansion, because expansion takes work, which means to get the same 1 Kelvin change in temperature, you got to give it more heat, because a part of it is being continuously used for expansion. But when you heat it at constant volume, all the heat that you're giving it is only being used to change the internal energy, which is change in temperature. Is that making sense? So specific heat at constant pressure is always bigger than the specific heat under constant volume. So there are two specific heats of a gas, and CV and CP. CP is always greater than CV, and the difference between them is the universal gas constant. Do you remember this? What's the number? What is the universal gas constant? 8.314. So CP is always greater than CV by that much for 1 mole. This equation is true for 1 mole of a gas. Be careful, that's for 1 mole. So if you write it as 1 mole. It's called Mayer's relation. And I may not have written it, but that's what it's called. It's called Mayer's relation. Is that much clearer so far? CV is the specific at constant volume. CP is the specific at constant pressure. And so if you take the ratio of CP and CV, will you get a number more than 1 or less than 1? CP is greater than CV, so if you take that ratio, will you get more than 1 or less than 1? Oh my goodness. You know, you only have yourself to blame for the low grades if you are getting low grades. CP by CV is called gamma. It's called the ratio of specific heats. It's always greater than 1. I'm going to show you for monoatomic gases. Okay, that's the cylinder and the piston that I was talking about, and I was trying to explain that when you heat it under constant pressure, the piston moves out, so it requires energy to do that work, okay? That's what I was trying to explain with that. Gamma is 1.67 for a monoatomic gas like helium, argon. It's 1.67, but for a diatomic gas like oxygen, nitrogen. What about air? So in a problem, if I give it to you as air, will you take it as mono, diatomic, or polyatomic? Air. What's air made of? Most of it is, that's what you thought. Most of it is nitrogen, and it's diatomic, and then followed by oxygen, which is also diatomic. So in a problem, if I mention air, gamma is going to be 1.4 because it's treated as diatomic. What about carbon dioxide? How many atoms in carbon dioxide? 3, CO2, and then in that case it will be 1.33. 3 or more than 3, it's 1.33, okay? So that is for a polyatomic gas. What is internal energy? What do you mean by internal energy of a gas? Are gas molecules moving? Yeah. So they have kinetic energy. And obviously there should be at least a small force between gas molecules, which gives it potential energy. So internal energy is the sum of kinetic energy and potential energy. Remember that. Internal energy is the sum of the potential energy and the kinetic energy of gas molecules. So that's what you mean by internal energy. And how is internal energy related to change in temperature? Now, I hope you don't take too much time on that question. So if I say the temperature is going up, what can you say about the internal energy? It's also increasing, right? Come on, are you here? So internal energy is proportional to the change in temperature. Temperature goes up, internal energy goes up. Temperature goes down, internal energy goes down. Keep that in mind. And the relation is actually, let's go back, the relation is internal energy is CV times dt. Why so? Because when you heat it under constant volume, all the heat you're giving is used for change in temperature. So that's why we have that formula, which is a very important one. Systems, when you talk about thermodynamics, there is an open system and a closed system. Basically, we're going to be talking about closed systems. What is an open system? An open system is something that can exchange matter with its surroundings. That means a gas leaking. See that the gas leaks in or leaks out. That is an open system. We're not going to be talking about open systems. You're only talking about closed systems. What is a system? What is a thermodynamic system? It's maybe just a gas or a mixture of gases, or maybe a gas and a vapor contained in a cylinder like this. And a system always has surroundings, and the system is separated by a boundary, which in this case is a cylinder. Are you getting what I'm trying to say? And what are we trying to do? What is our basic aim? I know, to get a good grade, but what's the basic aim of scientists when they do all this? They're trying to tap into the energy in a system and trying to use it. That's what human life is about. Using energy, right? Now, to use energy, shouldn't we know how much energy is there in the system first? So how do you measure energy? You cannot measure energy directly. Instead, you have measurable quantities like pressure, volume, temperature, and entropy. Have you heard of entropy? Yeah, we'll talk about that. These are called thermodynamic coordinates. So they give you an estimate of the energy in a system. So we can measure all these four, and when you measure them, you can calculate the energy in a system. Next up, we need to know how to use that energy. Are you following what I'm trying to say? First, we need to know how much energy is there in a system. Second, we need to know how to use the energy in a system. In a car, just to turn it to a reality, in a car, what's the actual working substance in your car? I think I mentioned it. If I have not, try. In your car, what is the actual working substance? Where do you get that energy from? I think I mentioned, that's why you quickly said air. Right, correct. Gasoline burns, the air absorbs heat, the internal energy of air goes up, and we use that internal energy. See that? To make it move. So that's what it is about. So that's about an open system and a closed system. Any questions there? Ask you. Can a closed system exchange heat with its surroundings? Yes. It can't exchange matter, but it can exchange heat. But it could be yes or no. If a system is completely insulated from its surroundings, completely insulated, then the change that takes place in that system is called an adiabatic change. So adiabatic changes are changes that take place in a system which is completely insulated or isolated from its surroundings. No heat exchange is possible. Heat cannot go from the system into the surroundings, neither can heat go from the surroundings into the system. That is an adiabatic process. All right? The opposite is called an isothermal process. What is the meaning of the word iso? Means constant. So isothermal means constant what? Temperature. So if a change takes place in a system at constant temperature, it's called an isothermal change. In fact, look at these four thermodynamic coordinates. If each one is a constant, you're going to give it a particular name. Let's start. If temperature is constant, what is it called? If temperature is constant, what is that change called? Isothermal process. Okay, thank you for those two who are answering. All right. If entropy is a constant, I know we've not talked about entropy, but that's when it's called an adiabatic process. So I've given you two ideas about an adiabatic process. What are they? Number one, I told you it takes place in a system which is completely closed in a sense, insulated from its surroundings. Second, just now I told you that in an adiabatic process, what is constant? Entropy is constant. Now, if the pressure remains constant, it's called an isobaric process. Has anybody heard about a unit for pressure called millibars? Bars? That's why it's called an isobaric process. If volume remains constant, it's called an isovolumetric process. Literally, I'm reading out the text to you because I know that you read the text a lot. Okay, so there are 4 types of processes, and these are the 4 processes. So I hope you understand that a thermodynamic system is defined by the 4 thermodynamic coordinates: pressure, volume, temperature, and entropy. And what does this show? Shows that internal energy is a function of those 4 thermodynamic coordinates. If any one of these changes, any one of them changes, what's going to happen to the internal energy? It's going to change. So internal energy is a function of those 4 thermodynamic coordinates. Here's a little snippet that you need to know. I already told you when a gas expands, work is done, isn't it? What's the formula for work? I think I should never ask you a question to save time. Force times displacement, actually. Say, take it as distance. Force times distance. All right? So there is a force applied on the piston. Isn't force pressure times area? Yeah. So a force is applied by the gas molecules, and as a result, it moves through a distance dx. Therefore, the work is force times dx. And then substitute for force as pressure times area, then you get pressure times A times dx. But what's A dx? What's A times dx? Anybody? A is the area of the piston, and dx is how much it moved. So what is A times dx? Come on. It's not the volume. It's the change in volume. Thank you. Isn't it? A moved through dx. It's the change in volume. So next step. It is the change in volume. So that's very important. Work done is the change in volume. So if you want to find the total work done, what you would do is you would go integral V1 to V2 of P dV. Total work done is given by integral the lower volume, which is the lower limit, to the upper limit P dV. Now, what do you know about integration? Do you know that integration obviously gives you an area? Yes. All right, in this case, what kind of graph are we talking about when we talk about the area? The graph should have, what are the axes of the graph? Come on. Pressure and volume. Volume on the x-axis and pressure on the y-axis. And if you take the area of that, you get the total work done, as you can see here. All right, let's slow down. This is the initial state of a system. That's the final state. Look at the graph and tell me quickly, is that an expansion or a compression? Thank you for those who are thinking. You know, the others can just sit there. What's happening to the volume? It's increasing. The volume is increasing. What's happening to the pressure? Decreasing, which means it's an expansion. And the work done during expansion is given by this shaded part, the area. That's clear. Now, this is actually called an indicator diagram because it indicates the process. Or it's called a PV diagram, right? And it's so useful. If the arrow was the opposite direction, what would you say? The arrow was in the opposite direction, then it was a compression. Because then the pressure increased. Come on. And the volume decreased. So you should be able to make that out. Work done, again, is the area under that graph. Means between the graph and the x-axis. That gives you the work done. So you can calculate work in 2 ways. You can either take integral or you can take the area. I want to define what is called a quasi-static process. You know, the opposite of infinite or infinite is infinitesimal. Infinite usually means very big in physics. Infinitesimal means very small. So when you say a quasi-static, actually quasi means false. Static means not moving. Falsely not moving. That means the process is so slow. Imagine that a gas expands from 1 meter cube to 2 meter cube and takes 1 whole month to do so. Isn't that a really, really slow expansion? that is a quasi-static process because it's infinitesimally slow. Keep all these definitions in mind to understand what's coming later. So here you see the pressure volume diagram. There is a system at A, initial state is A, and then it goes to B. What is that? What process is that? Quickly, name it. So what is that called? That's an isobaric process, constant pressure. Okay, what is this from B to C? Isovolumetric. So the system has gone from A to C, but it has gone through this route. Agreed? All right, second case, it could go straight from A to C along that path. Or it could go from A to D and then from D to C. Is the initial and the final states the same in all these three? Yes. But the work done, what do you say? Is the work done the same? Remember that work done is given by the area, so that should be an easy question to answer. Is the work done the same in these three processes? Come on now. No. Which means work does not depend only on the initial and the final state. It depends on the path taken. So work is called a path function. Work is a path function. What does that mean? Work depends on the path taken. That's an important point again. Work is a path, excuse me. Work is a path function, but heat is not a path function. Heat is not a path function. Work is a path function. So here's the question that I planned to ask, and I've already asked you. Is the work done the same? No, because work is a path function, right? You see how much time I'm spending on that point. Which means, you know what that means. It's going to appear in some form or the other. It won't be direct, but it's going to come. Work is a path function, while heat is not a path function. Are you all clear on that? Okay. Now we'll talk about degrees of freedom. Have we already talked about degrees of freedom? I think we did. Did we talk about degrees of freedom in this class? All right, so that will save some time. I've just shown the molecules of a gas. Molecules of a gas can vibrate and rotate. I've already shown this dance before. Now, monoatomic gases have how many degrees of freedom? Let's see if you remember. Number of degrees of freedom for a monoatomic gas. 3, because they can move along the X, they can vibrate along the X, the Y, and the Z. 3 degrees. But a diatomic gas, in addition to those 3, they can also rotate about the Y-axis and the X-axis. Are you watching that? This rotation is negligible. Why? Because the rotational inertia is going to be small. See that? Particles are not so far away from the axis. So that's why I've written all that. Look at that. It's negligible for a diatomic gas. But when it comes to a triatomic or more than that, it has 6 degrees of freedom. Do you get it? Okay? Any questions? This is called the law of equipartition of energy. Law of equipartition of energy. What does that mean? Energy is equally partitioned. Energy is equally divided amongst the degrees of freedom. Energy is equally divided amongst the degrees of freedom. And here is the formula. The internal energy per molecule per degree of freedom is 1/2 kBT. Stop right there. The internal energy of each molecule for each degree of freedom is 1/2 Boltzmann's constant multiplied by the absolute temperature. Now tell me this, if the absolute temperature is 0, what's the internal energy? 0. There's absolutely no energy. This proves that. Okay, so if that's the case for one molecule, can you give me the formula for 1 mole? If that's the formula for one molecule, internal energy of one molecule, what's the internal energy of 1 mole? How many molecules are there in 1 mole? What's that called? Avogadro number. So all you have to do is what? Multiply this with the Avogadro number, and you will get the internal energy of 1 mole, which I think is what I'm writing next. For 1 mole, you multiply that with the Avogadro number, you get it. Na is the Avogadro number. Is that clear? Now, but remember, this is for 1 degree of freedom, isn't it? Okay, so let's say we're talking about a monoatomic gas. How many degrees of freedom does it have? 3. So next up, can you write this? Internal energy per mole for a monoatomic gas. Go ahead. Internal energy per mole of a monoatomic gas. What would you do? You would multiply that with 3. That's it. And I just went ahead and wrote something. This product is called the universal gas constant. Did you know that? I think we used that before. Come on. We used that before. Kb is R by Na. So that's why Kb times Na is the universal gas constant. So for a monoatomic gas, because it has 3 degrees of freedom, you multiply that with 3 and you would get the formula. And I also decided to make it for n moles. Look at the change. I didn't want to write another step. So I said for n moles of a monoatomic gas, now I've got to multiply with 3 and with n, right? That's an important question for you. Go ahead and calculate, please. Quickly calculate the energy of helium, just right, energy of helium at 27 degrees Celsius. Energy of helium, energy of 2 moles of helium, energy of 2 moles of helium at 27 degrees Celsius. Now do not take like 15 minutes for that, please. Energy of 2 moles of helium at 27 degrees Celsius. You know, I wanted you to do this for one reason. Number 1, to make you move and think. Number 2, to show you that 27 degrees Celsius is about room temperature, isn't it? Almost there. Look at the amount of energy in that gas. And how many moles of helium do we have? Come on. 2 moles, which is how many grams? 1 mole of helium is how many grams? So you have 4 grams, right? Just 4 grams of helium is how many joules? Do you see where we're going to? That's a lot of energy. So next, if we could use that energy, we could really make stuff move. I wanted you to see that. Just a few grams of helium has that much energy. So imagine how much energy you would have if you had a lot more gas. And remember, if it was diatomic, it was going to be 5 by 2 nRT, isn't it? Come on, because it has 5 degrees of freedom. So when we use air in the engine, you get more. That's where we're going to. So the thing is, I couldn't throw formulas at you without explaining it. I know some of you would love that and turn this into a math class. No, I can't. So I have to tell you how we get there, which is a process. So finally, we come to the first law of thermodynamics, which is really simple but very important to understand. So I will take a few seconds to explain it. Here we go. So you have an ideal gas here. Wow. What is an ideal gas? An ideal gas has ideal behavior. An ideal gas is monoatomic. Take that down. An ideal gas is always monoatomic. That means there is no intermolecular forces. It's ideal, under ideal conditions. So you have heat coming into this, what's going to happen? And the piston is free to move. What's going to happen when heat comes in? A part of the heat will be used to increase the internal energy, and the rest of it will be used to do work for expansion, right? That's the first law right here. Q is the heat coming in. So if you take this to the other side, isn't it going to be the sum of the change in internal energy and the work done? Come on. That is the first law of thermodynamics. So according to the first law of thermodynamics, the change in internal energy of a gas is going to be the heat entering the system, take away the work done by the system. Now, there we have a big problem, because work could be done by the system or on the system. Correct? I'm going to give you a choice. A gas expands. Like if it was highly compressed and if something was holding the piston down, and suddenly you remove that restraining force, okay? Remove it. The gas expands. Is the system doing work, or are we doing work on the system? Simple. The gas is expanding. Come on. The system is doing work. Work done by a system is taken as positive because we are happy. We are thrilled. When somebody does work for us, we're like, oh, good. So work done by a system is positive. On the other hand, if you had to compress the gas, wouldn't you have to move the piston down? Now work is done on the system. And work done on the system is taken as negative. Right? Thank you. Work done by a system is positive, and work done on a system is negative. Here is an example. I mean, if Q is 600 joules and work done by the gas is 200 joules, find the change in internal energy. Go. You have 10 seconds. Q is positive 600, means heat is entering the system, right? Heat is entering the system. Work done by the gas is 200. What's the change in internal energy of the system? Go. I mean, I know the answer would either be 800 or 400. I know. In history. No, you're actually good. And I think this will be the last time I'll be teaching a double, because I couldn't plan it properly because one section has a lab in the morning, see? And then I can't. Double is good for me in the sense that I just need to lecture once, but bad for planning. So it's always going to be a single class, UP1, UP2, at least for the time being. Any questions on that? No? Good. Now, this is what I was telling you. Heat added to a system is positive, heat removed is negative, work done by system is positive, work done on system is negative. Didn't we talk about that? I think so. And then I think I'm giving you another example, or maybe the same one. I don't know, until it comes up. Okay, now it's work done on the system. Do you see that? Work done on the system means what? Compression. I use the same numbers. So the answer would be what? 800. And I'm not rushing. I'm not. There you go. Talked about that like 3 times now. Okay, so let's look at an isothermal process. What is an isothermal process? No change in temperature. So here you see 2 isothermals. One is at a lower temperature, the other is at a higher temperature. That's how an isothermal process will look like. There is no change in temperature. I want to ask you, do you remember any gas law that gives the condition under constant temperature? Any gas law? I mean, do you know gas laws? Name one. Boyle's law. What's Boyle's law? At constant temperature, there you go. At constant temperature, the volume of a fixed mass of gas is inversely proportional to the pressure. So Boyle's law, PV is equal to K, is defined under constant what? Temperature. That means that's the equation for an isothermal process. Pressure times volume is a constant. That is the equation for any isothermal process. But I also wrote it this way. Isn't PV is equal to nRT? Look at this. N is a constant, R is a constant. If you make T also a constant, then the entire right-hand side is a constant. So PV is equal to K. So I brought it out that way. That make sense? That's an equation for an isothermal process. Next, we need to get an equation for an adiabatic process. It's a long, long process. I won't ask you to derive it, but I want you to go through the steps. But before that, Let's calculate the work done during an isothermal process. Can you? Can you help me? How do you find the work? What's the basic formula for work we got? No. We went past that. Work was integral. Come on. V1 to V2, PdV, is it? We're going to use that. And then substitute for pressure. Isn't this the formula for, that's the ideal gas equation, right? And we're going to just substitute for pressure from there. Substitute for pressure. Why did I, under all these constants? So before I integrate, I've taken them out. What's integral dV by V? What's integral 1 by x dx? Natural log of x. Good. So you integrate, you get natural log of that. Those are the limits, and that's the final formula for calculating work done in an isothermal process. Find the work done when 1 mole of a gas expands to 3 times its initial volume at 27 degrees Celsius. That's my favorite number. I said, how many moles? 1 mole. What's the temperature? 27 degrees Celsius. And then I told you that it expands to 3 times its initial volume. So what is V2 by V1? 3. Go ahead, put it into your calculator. Let's see who gets the answer. Come on. Beat everybody if that's the right one. Let's hear a second person give the answer to make sure he has the right one. What's R? What's R, guys? What's R? 8.314. Okay, I hear different numbers.
What did he say?
He said 2,000.
2,740.
He said 2,000?
Mm-hmm.
So I got 2,740.
Oh, so I heard it wrong. All right, 2,740 joules. How many got that? Oh, 3 people. Look at this graph and answer this question quickly, please. On the same graph, you have an isothermal, AB, and an adiabatic, AC. Are their initial states the same? Are their final volumes the same? Are their final volumes the same? Yes. Are their final pressures the same? No. So what do you mean by slope actually? Slope, you know, is dy by dx. In this case, the slope would be dp by, help me out? So now, based on what I told you, or even otherwise, can you look at the two and tell me which one has a bigger slope? Is it an isothermal or an adiabatic which always has a bigger slope? And really important. That's important for us to understand how an engine works. Which one? Taking too much time. Which one has a bigger slope out of those two? AB or AC? AC. And I'm going to prove that the slope of an adiabatic is going to be exactly gamma times the slope of an isothermal. You remember gamma? What is gamma? The ratio of the specific heats. That's our next thing. I'm going to prove it. Now, to prove that, we have to find the slope of both. What's the equation for an isothermal change? Is this the equation for an isothermal change? Come on. So, I'm going to find the slope. Here we are. It's a multiple function, so when you differentiate, you know you have to hold one constant, differentiate the other, plus hold the other constant, differentiate the first one. Come on. Which is equal to? What is dk? 0. Because a constant doesn't change. All right, when you see that, you just rearrange. And you should be able to see, I'm going to cut out one step, you should be able to see that this is equal to minus 10. So you don't see it.
Oh, the same thing.
Minus P.
Minus P by, so the slope of an isothermal is negative P by, negative pressure by volume. Wait, do these two graphs have a negative slope? That's what the negative shows. Isn't that an expansion? If it's going from A to B or A to C, that's an expansion. Come on. So negative slope, and it's this. And then I will let you find the slope of an adiabatic. Okay? Equation. Oh, so that's not what I did there. Or hold on. First, and then we'll go back. Slope of an adiabatic is gamma times the slope of an isotherm. Important. And I'm going to find the slopes of both. And you will understand. I already found the slope of an isothermal. So write that one. Although I'm going to post all the notes. It's always good to write. So which one has a greater slope? An adiabatic, right? How many times? That of an isothermal? Gamma times. And is gamma the same for all gases? No. Remember the numbers I gave you, right? So you have to keep that. That could be a conceptual question. And then to find the slopes, here we are, the slope of an isothermal. We already found that. So let's speed it up. dP by, isn't this what we got? Now to find the slope of an adiabatic. There are three equations for an adiabatic. This is one. PV raised to gamma is equal to K. This is the equation for an adiabatic process. See the difference? For an isothermal, it was just pressure times volume is a constant, right? Here is volume raised to gamma. And then you can see what I'm doing there, or maybe you can. So what I'm going to write again. When you differentiate this, what do? P is a constant. Help me out. When P is a constant, what do you do with this? This is like x raised to n, which is nx raised to n minus 1. So that's why I'm going gamma, p raised to gamma minus 1, and then dv. Are you with me? Plus, next one. You hold the other one constant, and then go dp is equal to 0. Is that what I've written? Rearrange that. Cancel off what terms could be cancelled, and you would prove that the slope of an adiabatic is gamma times the slope of an isothermal. I could ask you to do that, of course. Slope of an adiabatic is gamma times the slope of an isothermal. So we're trying to get an equation for an adiabatic process. Don't try to write everything, try to understand. Are you familiar with that? What's that? Isn't that the first law of thermodynamics? Okay, tell me this. How would this equation change for an adiabatic process? What do you know about an adiabatic process? What do you know about an adiabatic process? It should be a completely insulated system, which means Q is 0. Very good. No heat can come in and no heat can go out. So Q is 0. If Q is 0, then it becomes this. And I hope you remember that internal energy was CV dt, isn't it? So I substituted this Q0 and work is PdV. So I rearranged that to get dt. That's my equation 1. I just got dt from that. Just rearranged, got equation 1. Second step, I start with, if it's 1 mole of a gas, we can write the ideal gas equation. Now someone like, where is the n? It's what? 1. Now from that, a little bit of calculus, I will get another expression for dt. Got it? Now I have 2 expressions for dt. Can I put these right-hand sides equal to each other? Because the left-hand sides are equal? Yeah. All right, so that's what I'm doing next. Put them equal to each other, a little bit of algebra, and then you will get the relation. Follow along, watch what it is. I've just taken the LCM and rearranged that, canceled out the same terms from both sides, and I have this expression. And then I'll tell you what I'm doing. I'm dividing each term by P, V, and CV. So out of this, these 2 will get cancelled. I'll get dP by P. The other one, I would get this. Do you know the next step? What is Cp by What is this?
Yeah.
That's gamma. Computers that won't stay awake. Okay, so that's gamma. So the next step, I think I wrote everything down, and then I take off from here. Isn't that where we stopped? Okay, so that's gamma, and then I integrate. When I integrate, you know that becomes natural log of P, that becomes gamma natural log of volume. There you go. Is equal to constant, which in effect is PV raised to gamma is a constant. Do you know how that happens? Did you know that A times B is actually log A plus log B? Come on. So I went back. So that's a reverse process. So that's how we get PV raised to gamma is a constant. Which of the four thermodynamic coordinates is a constant? Entropy. Which means pressure, volume, and temperature, all three change. Isn't that what it means? Therefore, taking two at a time, you should get three equations. Because that's an equation between pressure and volume, isn't it? So you can get two more by simple substitution of the ideal gas equation, as I'm showing, using PV is equal to RT and substituting, you could get that second equation, or you could get this as a third equation. All right, let's do a problem with an adiabatic process. Let's say that 1 mole of an ideal gas at 27 degrees Celsius, yeah, that's my favorite. At 27 degrees Celsius, 1 mole at 27 degrees Celsius is compressed to 1/3 of its initial volume. 1/3 of its initial volume. You heard me? Find the final temperature. Find the final temperature. Yeah, you know it's N is 1. T1, what is the initial temperature? Isn't that 300 Kelvin? Anybody here? What are we asked to find? T2? Final T2. Okay. What's the ratio of V2 to V1? 1/3. Okay. Now, what equation are we going to use? We need that equation for an adiabatic. And look, I didn't even mention that it's compressed adiabatically. Please. If I don't say that, you can't do it. You know what I mean? I should say 1 mole at 27 degrees Celsius is compressed adiabatically to 1/3 of its initial volume. That's when you use that. Okay. So what's the formula? Isn't this the formula that I gave you? Is this correct? Because we're talking about temperature and volume here. And therefore you would write T1, V1 raised to gamma minus 1 is equal to T2, V2 raised to gamma minus 1. And then substitute, rearrange, so you want T2 as the subject, so T2 would be T1 times V1 by V2 whole raised to gamma minus 1. And then I realized that I had to tell you what gas it was. 1 mole of an ideal gas. What if it was an ideal gas? I want to see. You know what? I have to tell you that it's adiabatic, and I have to tell you it's an ideal gas. What is the gamma for an ideal gas? I know I mentioned it. Maybe I did. I think I mentioned that an ideal gas is monoatomic, see? And therefore its gamma is 1.67. See, that's what you have to remember. So that means T2 is going to be 300 times V1 by V2 will become 3 raised to 1.67 minus 1. Can you calculate that and tell me what you get? So 3 raised to 0.67, which is how many Kelvin? 626 is what you get. Another person to second that? 626 Kelvin. Did you all understand what's going on?
So what was how did it become 3, the V1 over V2?
Because V2 over V1 is 1 by 3.
So,
This is the reciprocal of that, right?
yeah.
Hey, what if I had said 1 mole of an ideal gas at 27 degrees Celsius is compressed to 1/3 of its volume isothermally, and find the final temperature? It would be the same. It would be 300 Kelvin. And I've asked questions like that. That's supposed to be a conceptual question, but you want to know how many people use formulas and solve it? They won't read. Not you. I'm talking about the others who don't read the question, and they are used to this formula, so they'll go, TV raised. I said isothermally, which means the temperature is at constant. So be careful. I'm just checking if you're on my slides. We just finished off with this. We talked about this. Isobaric process. What's constant? Pressure's constant. Isn't that isobaric? And isn't it easy to calculate the work done in this case? Because you have a rectangle there, work would just be the constant pressure times change in volume. Hey, what kind of process is this? Oh, you can read. What is the work done? Yeah, you can read. But the question is, why is the work done 0? Because the change in volume is 0. Isn't it? Okay. Stuff like that, be careful. I'm building up stuff. Last, we're going to apply the first law of thermodynamics to all the 4 cases, one by one. Shall we? We've actually done it. This is a summary of the whole class. If it's an isothermal process, temperature is constant, so delta T is 0. Therefore, the first law, change in internal energy will become, you remember, change in internal energy is CV times dt, correct? If dt is 0, that's 0, so Q becomes equal to what? What does that mean? All the heat that's entering is being used to do in an isothermal process. Number 2, if it's an isobaric process, P is constant, the formula doesn't have anything to do with pressure there, so that doesn't change the entire thing. I mean, it actually has. Work is P times dV, right? But nothing becomes 0, it just is the same. Isovolumetric, volume is constant. So what happens to the work? 0. And therefore, all the heat entering is being used to change the internal energy. Last up, adiabatic process. We talked about all this. What is Q? It's an insulated system. Is heat entering in or leaving? No. So Q is 0. If Q is 0, then internal energy is equal to negative work. What does that mean? If you're not giving a system heat, and if it's doing work, where is it getting its energy from? From its internal energy. I mean, doesn't it already have energy in it? And if it's doing work, it's using that to do work. So what will happen to its temperature? Huh? It'll decrease. Okay, you know why I recorded this? Because this will be up on YouTube today. And I knew it was going to be an exhaustive lecture, so that's why I did that. Aren't you happy I did it? So go back and listen to it. Because there are lots of concepts that I talked about. And I had to do it on one day. I couldn't do it on like 3 days. We don't have the time for that, okay?